everyone loves to debate whether we're in a simulation. But here's what almost nobody points out. You don't need a grand programmer to analyze the universe, not because a programmer is impossible, but because it's simply not required to study what's happening in physics. So when you strip away all the noise, the universe boils down to two possible structures. Option one, a continuous universe, smooth space-time, infinite precision, filled with no smallest pieces. Or option two, a discrete information-based universe, reality built from finite steps and finite states, not created, not designed, just two candidate structures for the mechanics of reality. But here's the twist. We're discouraged from comparing them, not because science disproved one, but because the culture of science resists anything that challenges the continuous status quo. This isn't about rejecting a programmer, it's about saying a programmer isn't required to understand the physics behind a discrete universe. Scientists don't push back because discrete models are wrong. They push back because discussing them breaks the unwritten rules of the scientific culture, not science itself. Rule number one that it breaks, parsimony. Science demands the simplest explanation that fits the facts, but simulation talk, the mainstream version at least, adds a programmer, a motive, a reason, and those extra layers violate parsimony. So instead of separating structure from purpose, the whole idea gets dismissed outright. Rule number two, falsifiability. If you can't test it, scientists won't touch it. Simulation narratives with someone outside the universe can't be tested, so the entire concept gets thrown out, even the parts that are testable. And here's the real boundary. Physicists avoid drifting into theology or philosophy. Metaphysics, ethics, epistemology, aesthetics, they're ignored because those fields raise questions about meaning and purpose, not measurable mechanisms. So instead of separating the testable, discreteness, from the untestable, cosmic purpose, the culture of science silences the entire computational discussion, not by scientific objectivity, but by consensus and gatekeeping. So what do we do with this gatekeeping? Here's the pivot that makes the entire conversation scientific again. Remove the assumptions about purpose, not denying them, not disproving them, just saying they're not needed to analyze the mechanics. When you strip out the programmers, motives, or any cosmic agenda, what you're left with is something scientifically pure, computational ontology. The idea that the universe may operate on discrete information and deterministic rules with no metaphysical or theological assumptions attached. This doesn't say the universe is a simulation. It doesn't say it isn't. It just says the programmer question isn't required for the physics. And once you separate structure from purpose, computational ontology becomes a legitimate scientific model, but one you rarely hear about, because consensus culture still treats the whole topic. Here's where the silence really kicks in. Scientists say that a continuous universe doesn't need a creator. Physics just is. No purpose required, no philosophical or theological intrusion. But when you talk about a discrete universe, finite information, finite rules, suddenly some scientists claim that discreteness implies a programmer. That's not a scientific argument. That's a cultural reflex. If a continuous universe can exist without intention, a discrete universe can too. Both are just structures, but the scientific establishment is comfortable with the continuity and uncomfortable with discreteness. Not because discreteness is unscientific, but because discreteness threatens philosophical foundations they've been trained to ignore. So they apply a purpose-free logic to continuity and a purpose-loaded logic to discreteness. That's not objectivity, that's selective reasoning. So my one request here is let's be consistent. If neither model requires a programmer to analyze the physics, then both the continuous and discrete universes should be judged by the same rules. And those rules are the two that science actually rests on. Parsimony, the simplest adequate explanation. Which model needs fewer assumptions? Which one compresses the universe into the smallest description? And two, falsifiability, the ability to be proven wrong. Which model makes testable predictions? Which one risks being contradicted by experiment? These are objective standards. They don't care about consensus. They don't care about tradition. And they don't care whether continuity feels safer or more familiar. Once you remove purpose and stay out of theology and philosophy, the debate becomes purely structural. And that's when computational ontology starts looking dangerous. To consensus at least, not to science. Here's where the math flips the entire narrative upside down. Parsimony isn't just about vibes, it's about information costs. Homolograph showed that the simplest model is the one with the shortest total description. In this case, the fewest bits needed to specify the laws, the constants, the initial state, and precision. Continuous universes require massive information budgets. infinite precision, smooth fields, and endless real numbers. Discrete universes compress everything. Rules shrink into compact algorithms. Constants collapse into ratios. Starting conditions reduce to tiny seeds. Precision becomes finite. When you compare the two bit by bit, the computational universe is dramatically smaller by strict scientific parsimony. The discrete universe is the simpler model. Consensus won't say it, but the math does. Here's the part they really don't want discussed. A discrete universe is falsifiable, meaning it can be proven wrong. Here's how. Discreteness must eventually show up. If experiments keep pushing the limits and the universe remains perfectly smooth, the discrete model fails. Also, physics must not require infinite precision. If a theory demands true mathematical continuity, computational ontology breaks. And randomness must show patterns. If quantum randomness is fully Scheidt incompressible, the discrete model is disproven. Information caps must hold in the real world. If entropy or density exceed finite information limits, the model collapses. These are real, measurable, risky predictions. A continuous universe, by contrast, allows infinite precision and infinite complexity, which means that it rarely risks being falsified. So which model is truly more scientific? The one consensus favors, or the one that actually risks losing? One of the easiest ways consensus dismisses the discrete universe is by making it sound childish. Pixelated reality, like Minecraft? But discreteness doesn't mean blocky. It means there is a smallest unit of change. Not that the world looks like 8-bit graphics. Think about digital sound. A song is thousands of discrete samples, yet you hear a perfectly smooth wave. Think about video. There are millions of pixels in every video, yet your brain sees fluid motion. In physics, discrete rules running at incredibly fine scales produce pseudo-continuity at the human level. Curves, fields, spacetime, quantum behavior all can emerge from tiny discrete updates. So discreteness doesn't contradict our experience. It explains why reality is smooth even when it's built from finite steps. Here's the uncomfortable truth. Computational ontology isn't ignored because it's unscientific. It's ignored because it threatens the philosophical comfort zone of the scientific community itself. If the universe is in fact discrete, infinite precision disappears. The mathematical continuum is no longer fundamental. The equations scientists grew up with become approximations, and the foundation of modern physics becomes emergent, not sacred. That's not a scientific threat, it's a cultural one. Consensus is built on continuity. Funding, textbooks, prestige, all built around smooth space-time and real number equations. Discrete models aren't silenced by data, they're silenced by tradition. And when scientific culture suppresses an idea that meets parsimony and meets falsifiability, that's when you know it deserves a closer look. So here's the conclusion that's hard for consensus to swallow. Computational ontology isn't fringe. It's scientifically legitimate. It doesn't add a programmer. It doesn't imply purpose. It avoids theology and philosophy entirely. It fits parsimony better. It fits falsifiability better. It explains pseudo-continuity. It aligns with information theory, and it's threatened only by scientific consensus, not by scientific rigor. If science is truly about following evidence, minimizing assumptions, and embracing models that risk being wrong, then the discrete universe is not the outsider. It's the model that best follows the rules of science, which is exactly why computational ontology deserves a seat at the table in the conversation about the true structure of reality.